Hello, I am Elaine Daniele. I'm a chemical engineer at Petrobras. My three co-workers, Thiago, Otávio, and Tatiana, and I, research about gas lift valve failure. And now I'm going to present the comprehensive approach to tackle systemic failure in gas lift valves in pre-salt wells. For this work, you analyzed six gas lift valves, as you can see in those pictures. All of them were removed from the Santos Basin's pre-salt wells after failure. All six wells are natural flowing wells and produce an average of 70,000 barrels per day. So, if you are in natural flowing wells, why did you use gas lift equipment? Because in 10 years you expected to use them, and it's cheaper to install them at a first completion than to spend money on a future recovery. Five of these gas lift valves are a beta model, and just one, the well B, is one in an alpha model. I'm going to show you the difference in the next slide. All of them were of a high reliability class, meaning that the liquid discharge capacity of all valves is 2 barrels per minute. This valve had been inside the wells for 4 years on average. The time for cover operations for retrieval of the valves was shorter than the initially project forecast. What does it mean? More cost. In these pictures, you can see how the valves arrived on the onshore laboratory after their removal or cover. The gas lift valves of way A and B presented different residues, although the wells produced with similar water cuts. On the other hand, it can be seen that the wells C, D, and E presented a black residue, and FA did not present any residue at all. Another interesting information is that both wells, B and D, produced the same oil field to the same production unit. However, they presented different residue. What happened in each case? Why did the well valves with similar characteristics generate different residue? Here you have two examples of a high variability gas lift valve, alpha and beta model. The key of the high variability is the check valve. In alpha model, on the left, the check valve has 5 parts. There are the ring, an elastomer, the check seal retainer, a metal, a check dart, a check compression spring, and a nose retainer. The two first parts make a double sealing system, elastomer metal and metal metal. Another part you can see a number 6 is the venturi seat. In another type, the beta model, here in the right, the check valve has only 2 parts, spring and dart. The dart is connected with the venturi seat, and the dart and venturi has a different design. Also, it's important to say that in this beta model, there is only metal-metal sealing. In both cases, when the spring is relaxed, the valve will remain in a closed position. When annulus pressure is greater than tubing pressure, the spring is compressed, and the valve is in an open position. Now, I'm going to give more details on the well B case. In this slide, you can see a comparison of the internal components of well B valve, an alpha model, with those of unused one, a new one. You can notice the complete obstruction in the internal parts. This is the flow way outside and inside the valve. Here is the annular flow entry, and here is the flow to put into tubing. The same residue was found in the valve injection hole, which have direct contact with annulus fluid, and the valve nose, which have direct contact with tubing fluid. Here you can see in details the comparison of well-being internal parts and a new valve parts. All dart holes are blocked, as like the nose retainer and the venturi seat. After the initial completion, the well-being entrance was filled with a packed completion fluid up to 100 meters above the depth of the gas lift valve. The areas above the packed fluid was filled with diesel, to show here. At this moment, the pressure at the depth of the valve inside the tubing were estimated at 394 kg per square centimeters, and inside the annulus, 210. This represents a differential pressure of 184 in favor of the closure of the valve. In a test carried 1,000 days after, the pressure in the tubing and the annulus became 290 and 300 kg per square centimeters, which reached a negative differential pressure of 10. This was a strong indication that while the well was producing, the gas lift valve was open. So why did the annulus pressure go up? Probably, when the well B was kicked off, the tubing pressure decreased after the flow started. Because of that, the tubing temperature increased, and as a result, the annulus temperature also increased. There was only liquid inside the annulus, and the Christmas tree annulus valve was closed. Then, the diesel expansion resulted in annulus pressure increasing. When the annulus pressure became greater than the pressure inside the tubing at the depth of the valve, the gas lift valve opened and the packed fluid met oil plus water. After pressure equalization, the well behaved like a U-tube. When and how was the valve failure discovered? In the chart you have tubing pressure in dark blue, annulus pressure in red, Christmas tree tubing valve in yellow, Christmas tree annulus valve in gray, and shock valve in orange. About the valves, when is it open, we have the value of 1 in the right ordinate axis. When it's closed, you have 0. Both Christmas tree valves have the same open and closed behavior. The annulus tubing communication was identified during an expected well closure event. The annulus Christmas tree valve was open, and then the water cut was about 12%. We expected that the tubing pressure would decrease and the annulus pressure would decrease. However, as you can see here in this chart, what happened was that after the closure of the well closed the choke, the tubing pressure in dark blue increased and the annulus pressure in red followed this increase until there was a pressure equalization. And that is another evidence for the hypothesis presented in the previous slide. A transient multiphase flow simulation was performed considering the kickoff condition. The results is shown in this chart, where you have the pressure trend in the left, the flow rate trend in the right. The tubing pressure is represented by the blue line, the annulus pressure is represented by the red line, and the gas lift flow by the purple line. The simulation showed an initial transient with high discharge liquid flow due to the large drawdown at the well kickoff. It showed that the fluid flow was from the annulus to tubing. Also, the simulation showed the effect of diesel expansion and subsequent pressure equalization between the tubing and the annulus pressure, which indicates that the gas lift valve was open. The simulation also showed that the liquid flow rate through the gas lift valve never exceeded 2 barrels per minute, which is the critical technical limit of this valve model. Now I'm going to analyze the residue and composition of produced water and fluid. The residue found in well B gas lift valve were analyzed by X-ray diffraction, and the sample shows mainly strontium and a smaller proportion barium. The produced water contained barium and strontium in high concentration, sulfate 2, like you can see here in this table. The bucket fluid used in well B was a brine sodium chloride with a standard corrosion inhibitor. During our operation, to avoid really downtime, it is common to use seawater instead of potable water in the formulation of completion fluid. Unfortunately, this brought to the completion fluid a high concentration of sulfate ions from seawater. It is believed that strontium ions from the produced water met to the sulfate ions from the completion fluid and generated the strontium sulfate. In high pH value systems, such as the completion fluid environment, the reaction is inversed. The same is true for the formation of barium sulfate. The saturation index reached a high value, making a suitable condition for scale deposition. We know that the mixture of seawater and produced water is considered the main cause of scale deposition in oil fields. Differences and similarities in cases of well A, B, and D. When the gas lift valve of those wells were analyzed, similar residues between at least two of them were expected, since the wells have several similar properties, like you can see in this table. Well A and D gas lift valve are a beta model, and well B is an alpha model. Water cut values are similar in well B and well A. Another similarity the fact that well B and D, although with different water cuts at the time, are from the same oil field and produced to the same unit. However, the residue from these three valves presented different characteristics, and only the well B gas lift valve presented the scale. The well D gas lift valve residue was composed mainly of iron, with a small concentration of barium. The well A gas lift valve did not present residue on the outside of the valve frame. However, it was not possible to dismantle it. There was no tool for it in that time. Thus, it is very unlikely that no residue deposited in the internals of this valve, since it presented check valve stuck in an open position, like in this picture. This indicates the valve failure, and one possible cause of this type of failure is residue deposited in the check valve. The completion fluid used in all three cases is remarkably similar. However, well A was completed with nitrogen in the endless, differently from well B and well D that were completed with packet fluid and diesel. The fact that well A was completed with nitrogen in the endless avoided contact of the completion fluid with the produced fluids, which would allow the formation of compounds that could be deposited and cause the valve failure. Conclusion. The fact that corroborated the deposit of barium and strontium sulfates in well B and not in well A are the great presence of ions in well B, and the fact that well B was completed with nitrogen in the angles, thus avoid the mixture between the produced water and completion fluid. The hypothesis that the failure of free gas lift valve may have originated in the well completion phase is weak, since the critical liquid discharge flow of 2 barrels per minute is considered to have been respected during this phase. There are indications that well B operated with the gas lift valve was open. It probably happened due to the contact between the completion fluid, basic pH, and high concentration of sulfate ions, and produced water from the reservoir with high concentration of barium and strontium. Recommendation for upcoming recovery. It is recommended to study the viability of installing blind valves. This is especially important in wells where the gas oil rate is expected to reach extremely high values, and thus make, even after the increase of water cut, the use of artificial lift unnecessary. It is also recommended to complete the wells placing nitrogen in the annulus instead of packet fluid and diesel. Thus, in case of gas lift failure, the contact between the packet fluid and the produced fluid can be avoided. Also due to expandability of the gas, it would be easier to maintain the pressure inside the annulus. Recommendation for well and production. The pressure equalization between the annulus and the tubing at the depth of the gas lift valve does not guarantee valve closure. At least a differential pressure of 7 kg per square centimeters is required to ensure the closure of gas lift valve. Monitor the annulus pressure, repressurizing the annular volume when necessary. If the gas lift valve is already stalled, check the absolute pressure and the differential pressure that the annulus is subjected to. There is a possibility that the valve is open, making possible the contact between the annulus fluid and the produced fluid, which brings a high-scale deposition risk. Elaborate a flushing procedure with diesel as a first step after determining the annulus tubing communication. It aims at removing small residue that can be accumulated in the valve, which may prevent the closure of the check valve. Monitor the water cut blow and wells with gas lift valve. It's important to ensure the high dosage of scale inhibitor. An improvement in chemical injection system would bring great gains to the integrity of gas lift valves and other equipment. New studies and transient simulation are necessary to better understand the failure mechanism of the gas lift valves under A and D. For the accomplishment of this work, the support and teaching of Daniel Maia were essential. The author thanked Petrobras for allowing the publication of this article.